Adversaries bypass traditional multi-factor authentication deployments using automated adversary-in-the-middle proxy architectures to hijack active session states instantly. Reverse proxy tools like EvilJinx intercept credential submissions and session tokens by acting as a transparent bridge to legitimate identity providers. When a target logs in through a phishing link, the proxy transparently relays the authentication handshake to the genuine authentication server. The identity provider validates the credentials and issues a valid session cookie, which flows straight back through the attacker infrastructure before hitting the user. The adversary extracts this authentication cookie from the hypertext transfer protocol headers, allowing them to clone the session on an independent device without completing any multi-factor prompts. To mitigate adversary-in-the-middle vectors completely, application developers must transition from phishable factors to phishing-resistant frameworks like Fast Identity Online 2 and WebAuthn. WebAuthn binds the cryptographic credential to the specific origin domain name registered during public key generation, preventing credential reuse on spoofed target domains. In your server-side application verification logic, you must validate that the origin property inside the collected client data JSON matches your fully qualified domain name exactly. Reject the assertion immediately if the domain string mismatches, ensuring that a token harvested by a proxy domain like login.security.com fails authorization.
Another widespread bypass method relies on multi-factor authentication fatigue, where threat actors trigger a continuous stream of push notifications to overwhelm targets. Users eventually tap the Approve button out of frustration or distraction, inadvertently granting the malicious login attempt full access to the target infrastructure. You can remediate push notification spam programmatically by implementing context-aware number matching verification within your mobile authenticator application workflow. The web authentication frontend was generate a random 2-digit integer and display it prominently to the user attempting the login action. Simultaneously, transmit this expected number securely via an encrypted payload to the mobile push service as a verification constraint parameter.
The user must manually type this identical integer into the mobile application prompt, preventing blind approvals from remote malicious login requests. Beyond push exploitation, session hijacking via malicious info-stealer software targeting endpoint browsers bypasses multi-factor checkpoints by harvesting existing cookies directly. Once an endpoint is compromised, attackers copy the localized cookie database containing active tokens, bypassing all initial login authentication barriers completely. To secure session states against data exfiltration, configure your web application cookies with the strict secure hypertext transfer protocol only and same site attributes. Implement continuous token rotation by issuing a new unique session identifier with every incoming sensitive application request or structural state change. Your backend must invalidate the old session token instantly upon generating the replacement token, minimizing the usable lifespan of any stolen cookie. If an incoming request presents an outdated or previously rotated session token, your backend database architecture must immediately flag the entire user account as potentially compromised and execute a cascade function that terminates every single active session token assigned to that identity. Application developers can also implement advanced cryptographic device binding strategies by directly tying the validity of session states to unique client transport layer security channel identifiers or specific hardware cryptographic device fingerprints collected during initial authentication handshakes.
Calculate a highly granular internal client profile hash on your secure server infrastructure using a combination of incoming headers such as user agent strings, acceptable network subnets, regional localization configurations, and the specific negotiated cryptographic cipher suites presented by the client browser. If an incoming session cookie suddenly shifts to a completely different user agent profile or displays an impossible geographic routing trajectory within a short timeline, your routing layer must intercept the request and trigger an immediate adaptive step-up multi-factor authentication challenge.
Short message service-based multi-factor authentication remains incredibly vulnerable to complex subscriber identity module swapping attacks, where sophisticated threat actors successfully leverage social engineering tactics or corrupt telecommunication provider insiders to transfer target phone numbers to tracking devices.
Once the telecommunication database record is altered, the underlying telecom infrastructure routes all incoming one-time verification code text messages directly to the adversary device interface, entirely bypassing any local protection mechanism configured on the victim original hardware application profile. To resolve this systemic cellular vulnerability, software engineers must eliminate short message service code options entirely from their primary authentication policy configurations, substituting them exclusively with secure time-based one-time password algorithms managed within local cryptographic vault software.
When programming time-based one-time password verification backends, you must ensure that all user seed verification secrets are encrypted at rest within your database infrastructure, utilizing authenticated encryption with associated data standards like Advanced Encryption Standard 256 in Galway counter mode. Enforce a strict and highly aggressive rate-limiting policy directly on your token validation endpoints to prevent automated distributed brute force scripts from attempting to guess the current valid 6-digit multi-factor authentication token sequence before the standard time window expires.
Restrict your server-side token validation window to a maximum tolerance of exactly one previous and one future time step while concurrently tracking and rejecting previously utilized tokens to permanently protect the application against potential multi-factor intercept replay attack vectors. Another highly sophisticated threat vector gaining traction involves illicit OAuth consent phishing campaigns, where threat actors construct deceptive application registration portals that trick authorized target users into granting broad corporate data access and persistence permissions to a foreign malicious application.
Because the unauthorized app integration relies directly on persistent programmatic token permissions rather than continuous standard user interactive login pathways, it completely bypasses all subsequent multi-factor authentication verification checks during background data exfiltration cycles performed by automated attacker scripts. To fully protect your internal OAuth token architecture from exploitation, your backend authorization verification engine must strictly validate incoming redirect uniform resource locator strings against a rigid, non-wildcard server-side whitelist of absolute fully qualified domain names. Application development teams must programmatically enforce the fundamental security principle of least privilege by hard-coding maximum limits on permissible scopes during application registration, ensuring that third-party integrations cannot request or acquire wide-reaching access across your enterprise resource boundaries.
Adversaries also target highly durable, long-lived refresh tokens to maintain persistent system access across backend APIs, allowing them to continuously regenerate fresh access credentials long after the initial short-lived user authentication session tokens have naturally reached their expiration limit. Configure your enterprise authorization server engine to execute continuous refresh token rotation protocols, which programmatically invalidate the existing refresh token and issue a brand new, unique cryptographic token pair every single time a client application requests a fresh, short-lived access token.
Static backup recovery tokens are frequently targeted by threat actors because they are routinely stored in plain text files by end users or generated with dangerously low entropy, providing a weak alternative authentication pathway that completely subverts active multi-factor checkpoints. When implementing secondary recovery mechanisms, software developers must generate all backup codes using a cryptographically secure pseudo-random number generator, producing high-entropy alphanumeric strings that are statistically impossible to predict or brute force over millions of distributed computational iterations.
Never store these emergency recovery codes in plain text inside your production persistence layer. Always apply a resilient password hashing standard like Argon2 ID before writing the payload to your data storage cluster to ensure absolute confidentiality against internal database exposure. Finally, secure your multi-factor user configuration adjustment endpoints by mandating a strict re-authentication sequence using the active high security factor or verified out-of-band validation processes before allowing any structural modifications or removals of registered multi-factor devices.